Final presentation of the morning. I'd like to welcome Chris Thorne from the Energy Technology Institute, ETI. Chris coming. Chris is going to present on increased real-world fuel efficiency. And for those who are not familiar with Chris, he's a Chief Technology Officer for heavy-duty vehicles at the Energy Technologies Institute in the UK. He's responsible for ETI's technology development and demonstration program, which is designed to increase heavy-duty vehicle efficiency by at least 30%. He joined the ETI from Caterpillar in November 2010, and after having worked in a number of positions responsible for engine design, development, and integration. Chris, thank you very much for joining us, and go ahead with your presentation on real-world fuel efficiency. Thank you.
Thank you very much. So I've actually tried to adapt my presentation to kind of pick up on some of the points that have been raised earlier in the kind of last couple of days we've had. So hopefully that will kind of try and knit together some of the discussions we've been having. So what I'd like to go through in my presentation is just to say a little bit about what the ETI is and what it's trying to achieve with heavy-duty vehicle efficiency, and also try to kind of say a little bit about where the heavy-duty vehicle industry fits in the context of whole energy systems. So the ETI kind of comes at it from that perspective. And I think that's quite an interesting view to try and say, okay, this is not just about trucks. This is about everything that we kind of have within our societies, heating homes, generating electricity. But what part do we have to play, or could be played, in kind of meeting our climate goals? Then talk a little bit about what we're therefore trying to do, and then kind of talk about next steps and conclusions. And hopefully throughout the presentation, there'll be some things that will entice you to come and talk to me in the lunch break and kind of discuss some of this further. So just a little bit about what the ETI is. The ETI is a public-private partnership, so it's kind of a collaboration between the UK government and 5 energy companies, which you can kind of see the logos on the screen. And we were set up to try and help accelerate low-carbon technologies into the market. Not necessarily to create final products, but get technologies from research and through to the point where OEMs and big companies felt more comfortable to invest their own money. And we were also kind of set up, to take that shared risk, but to take calculated risks and to do the things the industry weren't naturally doing currently for themselves. So it's not about working on technologies that the industry is already working on, but to try to do things in the margins, but things that we felt would have a big impact or big potential impact. And we work across the full energy spectrum. So we work in carbon capture and storage, nuclear power, biofuels, offshore renewables, the whole kind of gambit. But obviously today, I'm talking about our efforts in heavy-duty vehicles. So I talked about, we try to kind of spot technologies and take calculated risks and support things which would have a big impact on the energy system. And we have various tools at our disposal to help us do that. One of them is the fact that we kind of create a system model of the energy system within the UK. And we use that to say, okay, within 2050, we'll have an estimate of a population. We'll have an estimate of our needs for transportation, for heating, for electricity. And then we use this tool to design the energy system in 2050. And 2050 is important because the ETI has enshrined in law a set of carbon budgets that increment down between now and 2050. And in 2050, we need to have a greenhouse gas kind of CO2 equivalent, which is 80% less than 1990. So that's what we're targeting. So, Will was trying to predict next steps in engine design and kind of postulating what might happen. We're trying to do 2050 for the whole energy system. So there are some error bands in some of what we'll say. And so on that basis, what we do is also very probabilistic. So there is not one answer. There is a range of answers, all of which are plausible. But what this tool allows us to do is to effectively look at what's the lowest cost way of the UK doing that. And obviously some of these charts are eye candy rather than particularly readable, but the big one is the total system cost. You can see that's a probabilistic number. And it's not horrendously high, actually. And through this process, we can kind of get an estimate of what 2050, 2040, 2030 carbon price might be. And I think I'll show some curves on that in a moment. I think one of the things to point out is one of the ways in which ESME solves the problem is it actually takes biofuels, combines that with a carbon capture plant, and generates negative emissions, which is that red bar that kind of sits below, on the bottom left chart, sits below the zero line. And that allows transport sector to still emit more than its kind of fair share of emissions. And the reason ESME does that is because decarbonising trucks is expensive. But certain things have to happen, and you'll see that on the next slide. So it's just a little bit about, how we generate insights and perspectives on the whole energy system. And it's quite use case centric. Having a UK-focused view is not, it's kind of hot in politics at the moment. I'm not promoting that. We recognise that the heavy-duty vehicle industry is a European, if not worldwide, industry. And so we can't think about what works in the UK only. We have to think about, what works in Europe, and therefore what might European trucks have in them, and therefore because we're a net importer of trucks. So this is a slide I've added at the last minute based upon some of the discussion that went on yesterday from the Volvo presentations and the JRC presentations, where we started to talk about, okay, there's certain things that we can do which are make sense based upon the price of fuel. So they pay themselves back in 12, 18 months. There's some things that perhaps sit on the borderline where, if we start reporting, we'll see a little bit more certainty of pull through of technology. And what we've tried to start to do is to say, okay, can we create a design space which we could present back to the industry to say, if you could do something in this space, you would be competitive with all the other things that could be done within the energy system. So effectively doing like a comparison between what's the cost of abating carbon in a truck versus building a nuclear power station, or what's the offset between an offshore wind farm and a truck. So the charts are a little bit complex, but think of it as an opportunity for the industry based upon carbon price to do as much as it can. And in this, I show a couple of charts. So the one on the left has that, you remember I said that there's some negative carbon gets created by growing biocrop, pulling CO2 out of the system, burning it, capturing the CO2, and then injecting it under the North Sea. That's the one on the left. If I take that ability away, I generate the curves on the right. And what you have on the axes is, on the vertical axes, what's the probability that it gets deployed by 50%? So what's the probability of mass market take-up against the cost of a truck for various carbon performances? And what you see is that the system, it does really like a zero carbon truck. And it's very likely that would see mass market adoption if you could make one for just under £200,000. So even in the perfect energy system, zero carbon in 2050 has a significant value, and that value is 2 to 3 times more than today's kind of thought process around truck cost. So there's kind of an opportunity for a paradigm shift in our thinking about how much cost we put on an individual truck. If we think of a current price plus an increment, you can convince yourself not to do anything. 2050 is a slightly different picture. If we design a non-optimal energy system and we don't do everything that's minimal cost, which is likely, and I take away one of the key technologies, which is carbon capture and storage, and that's plausible because actually the UK has got 100 years worth of carbon capture storage within its geographical area under the North Sea, but not every nation has that as a capability. Suddenly what you're willing to pay for your zero carbon truck goes up to 300,000 with a high degree of certainty. Remember, ESME's probabilistic, so this is all kind of got all various ranges of costs in. So we're relatively sure that you can spend a lot more on a truck in that scenario. And the other thing you'll see is trucks which have an instance of 0.04 kilogram CO2 per ton kilometre number, suddenly the systems, they're not wanted. So with CCS, there is a plausible scenario where you can use hydrocarbons. You have to use them very efficiently, but you can use hydrocarbons, maybe gas, because of its inherent lower CO2 value. In this alternative future, the system doesn't want them. It can't solve if you're emitting from trucks. So I think I just wanted to add that as a perspective. It's actually a piece of work that we've done off the back of a conversation we had with DG Climate, where they kind of wanted to understand what that kind of 2050 looked like. The last thing on this chart, because I need to get to some efficiency technologies, is that obviously I'm showing you 2050. So the question is, when do we go from the current kind of view on cost, which is fuel driven, where do we shift to this kind of potential, different future? I think that's probably 2030, 2035 timeframe. So really, I think in two time steps. One is, between now and 2035, 2040, how do I be as efficient as I can? And then post that point, how do I transition into something that's even lower carbon again? And at that point, I probably need to think about other energy vectors, other sources of energy other than hydrocarbon. So hopefully that ties into some of the discussions we had yesterday, and is a useful input. So what I'm going to talk about now is more about our thought process between now and 2035, 2040, and the work that we're doing to try and inform and influence that time period. Because obviously from a Paris point of view, it's not just what we do in 2050, it's also the amount that we emit on the journey between now and 2050. So as we look at heavy-duty vehicles, you can see that actually there's kind of a range of emitters. The biggest proportion is on highway, but off highway is significant, and therefore we've felt that we've had to tackle both on and off highway. Marine's not included in this chart, but we've also doing work in marine as well. So we're trying to take a holistic view and tackle the CO2 performance of all of those different sectors, and trying to use common technologies to achieve that. So based upon that, we created a program. We kind of set ourselves the objective to achieve at least a 30% reduction in the greenhouse gas emission. And what we wanted to do is create a program which didn't constrain the engineers in achieving that goal. So it allowed new vehicle concepts and simultaneously new technologies to be developed. And then we want to pull that together into scale demonstrations, so physical vehicles and vessels that then show that performance is achievable. And hopefully through those demonstrations and that work, convince the supply chain and the OEMs that, okay, there is something of interest here and there is some things that we'd like to deploy and put into the market. And through that, therefore, achieve our overall aim, which is a meaningful impact to the greenhouse gas performance of heavy-duty vehicles. So just to take you through the steps that we went through, this chart's kind of got land and marine, but obviously for today I'm going to focus on the land side of things. So we created high-fidelity models of 6 vehicle archetypes, both on and off highway, and tried to use these computer models with input of real-world cycles to understand what's the best set of technologies that we think we can come up with to deliver our 30% target. That concluded at the back end of 2013. And then off the back of that, we then commissioned a range of technology development projects. So it's probably worth pointing out that the ETI doesn't do all the hard work. We put calls out for people to bid in on them, and then people help us to develop those technologies, and we fund that work. And so we've done a range of projects which are listed up there. Too much to go through today, so I've picked out one as an example, which is the Continuously Variable Transmission project. We've also done, particularly pertinent to this conference, an SCR project. Some of that links to Jonathan Wilson's work from Loughborough as well, so I'm not going to go through that in too much detail, and I'd kind of welcome a discussion after this or with Jonathan on his work, which he presented yesterday. And then those projects all kind of culminate in a systems demonstration, which is ongoing. The final version of that demonstration will be in 2018. And currently, that demonstration will be on an off-highway truck initially. And this is just to say that hopefully the OEMs can see, well, look, the technologies have been de-risked and have been developed, they're mature. I can think about adopting them into my product cycles. The supply chain can see, okay, I have a value, as part of a system, integrated system, so they can value individual technologies much better. And hopefully that gets everybody kind of moving along towards a lower, a higher, a better fuel consumption future. I think this slide was already in here, Will, but I haven't added this in as a consequence of the previous presentation. But I think we all agree that real-world usage and understanding how things are really used is fundamental to selecting the right technologies. And we've really seen a sensitivity to that through our work. And so we have a project at the moment where we're trying to get significant, thousands of trucks worth of data to understand, okay, what is really going on? And how do we develop the best technologies for that? So we've tried to really take a systems engineering approach, coming at from the top level and working our way down. And I think this actually, again, linking to some of the other conversations, I think as we've gone through this work and seen what 5G might do to the telematics market, and obviously linking to the earlier presentation about OBD and the fact that CARB want the NOx sensor reading to be made available, I think from a legislative point of view, you can start to see, well, actually, there might be market-based measures which become more powerful than some of these other legislative processes. We're already seeing organisations back-calculate the efficiency of the powertrain using telematics data and being able to share that and compare different trucks and different manufacturers and offer advice about what's the best truck to buy based upon this sort of data. So a very similar outcome to what Vector is trying to achieve, i.e. informing the consumer better about their choices. I think we can see, some of these disruptive communication technologies and reporting through OBD could deliver the same impact. And maybe do it in very bespoke ways to the end consumer, a much better experience. So I talked about how we kind of use computer models to come up with optimal vehicle architectures and technologies. The vehicle architecture we ended up with looks like this, and we deployed that across a range of different vehicle types. So it's very similar in the bus, it's very similar in the off-highway articulated quarry truck, very similar in the HGV. And deploys, at its heart, a continuously variable transmission. And what we found is when you look at that as an isolated single technology, it looks like a pretty bad thing to do because it's inherently less efficient than, an automated manual transmission. But when we looked at all the other side benefits and system benefits we get from that CVT, we started to kind of add benefit on benefit to say, well, actually, we think there's something in this technology, even for long haul on highway truck. And some of those symbiotic benefits, or system benefits, are listed on the slide on there. And so what we're now trying to do is to work out what's the quantities involved in those trade-offs, and does it win out as in terms of a quantity. And the solution includes stop-start, and some of that's enabled by engine off, air conditioning functions, etc. As well. And you can kind of see our high efficiency SCR project, kind of how that knits in as well. So I'd just like to kind of take the CVT as an example of one of the projects we've done. Obviously, I also listed earlier on all the other ones we've done. If you're interested in any of that, then please come and talk to me during the break. But we've worked on CVT, just showing you there the vehicle types that it best applies to. And you can see that it can be leveraged across quite a wide range of vehicles. And that's great for us because we get to invest once and hopefully see that benefit deployed across a wide range of vehicles. And we were obviously trying to get it as efficient as possible and provide that positive end user payback. So obviously I talked about carbon price at the beginning. That's kind of a 2035 onwards conversation. Right now we want to deliver efficiency between now and then, which is market feasible, 12 to 18 month payback. And that's what we've been targeting with this. And the whole objective is to minimize the technical risk to a tier one or an OEM. We want to create an engineering package that we can hand over and someone can do something with. So just to say a little bit more about the CVT, it's an input coupled split path CVT. So it kind of has 4 speed ranges. You can kind of see down the bottom that it uses a variator. So you get a continuous ratio range. Once you've launched and the launch clutch is engaged, you get a continuous ratio range all the way through, but you're effectively handing off between different ratios and you're sweeping a variator to achieve that continuous transmission ratio. Currently, the reason it's hydromechanical CVT, currently a hydraulic variator, but I think as electrical machines improve, then there's the potential to replace that with a more efficient electrical variator and gives a nice step forward into an electrified future, potentially. One thing about what I'm going to show you is I'm very aware that a lot of people come with new technologies and they can come across as snake oil salesmen. The numbers that I talk about are numbers that we have achieved in our prototype. That prototype has a ratio range of nearly 30, so it's very much set up to achieve the off-highway ratio ranges needed. You do get some trade-off with efficiency, but the efficiencies I'm showing are the ones we've got. We hope to improve those as we go forward, and we're currently working on that as we speak. So this is just to show that it exists. What you have on the left is a C71 or a 1206 Perkins engine. This one's painted yellow, so it's a C71. A very nice engine, by the way, because I'm also an ex-Perkins alumni as well. And that's mated to the CVT. Now the CVT, you might be worried about the size there. The CVT is designed for up to a 13-litre engine. It just happens to be married to a 7-litre engine in this instance. Before you got too worried about the size of the transmission. And it's in an iron case. It's very much a prototype. And then on the left, you can see it installed on a powertrain simulator rig. So this is a 4-quadrant AC machine, and it can simulate effectively the lower powertrain and the longitudinal dynamics of the vehicles. So we can pretend we're an articulated quarry truck, or we can pretend we're a heavy goods vehicle and kind of develop the technology that way. So I just wanted to point out what the various bits are. I've got a video now just showing this thing operating, but it's a bit hard to see the different elements in that video. So hopefully this will work. So again, just a shot of the test cell. And then you have, apologies, it's not brilliantly visible, but you have left and right pedal at the top, and then vehicle speed, target, and achieved in the bottom chart. And you can see RPM, etc. And this is just to show, just to prove it works, or it is, it's real. So it's effectively currently going through a quarry truck drive cycle. You can see it's got gear on there, which is a bit odd. It's a CVT, but this is just showing you which of the 4 ratios it's in as it sweeps the variator. And you can see engine RPM. And so on. And RPM does change. You can calibrate it in a range of ways. So, currently we would be targeting the optimum lowest BSFC running line of the engine, but you can make individual choices about how you optimize your system. And because it's got a big ratio range, you can run any engine speed for any ground speed you like, effectively. So one of the big benefits is the de-speeding you get from this transmission. And it's also very fast reacting, so you can run very low road load RPMs, and if you do hit an incline, you just seamlessly change ratio. There's no bogging down issue or kind of chasing the next gear. So this is just trying to, it's an early quantification. We're doing a lot more work on this with AVL currently, so we're ongoing with that project, and they're helping us effectively do some due diligence on this early assessment and do a much better, well-rounded assessment for on-highway. So what we've said is the most challenging application for the CVT technology is heavy goods vehicle long haul. If we can make it work there, it will be brilliant everywhere. So we focus that as a challenge and an opportunity. And this is just a little bit of work where we've taken a baseline truck, which is hopefully representative of Euro 6, showing the transmission loss and the engine loss. When we take that current engine and apply the CVT, things get a little worse because the CVT is less efficient. Remembering this is the prototype CVT, not where we think we can get it. But when we bring in some of the engine changes that the CVT enables, CVT gives a hotter average exhaust temperature, so we can lean on the SCR more. It gives a much narrower running line for your turbo machinery, so we can deliver much better turbo machinery performance. And so when you get that, you kind of get the bar chart on the right side, and that shows that actually now I can get to a position where I'm in a net gain. So it's just trying to show that we have to look at it as a system, and as we do that, we still see opportunity for this technology, even in the harshest application, which would be long-haul heavy goods vehicle. So in terms of next steps, I think we want to going to conclude this real-world kind of how trucks really use project this summer, and we'll feed that into our technology assessment. We'll conclude the physical testing of the various powertrain elements on the powertrain simulator rig. That will also all go into a vehicle test. We're doing a heavy goods vehicle or long-haul truck focus modelling exercise with AVL, and that will conclude early 2018. And we also have some opportunity to put some of what we want to, some of the tests that AVL would like us to do onto that powertrain rig as well. So we can do some testing, which is HGV specific. Look into electric versions of the transmission and try to engage the OEMs and the tier ones in what we're doing so that they can give us yes or no, you've not thought of that, give us some feedback on what we're trying to achieve and engage in it. And we can do that in some various levels, which shouldn't be too burdensome for the OEMs and tier ones. I think the other thing which I haven't mentioned, which again links to an earlier conversation, is we've also been doing some work on gas, natural gas as a fuel. And we will have what we call an insights paper coming out in a couple of months, where we've done a full well-to-motion study of the implications of gas. So that's just a shameless plug for that report, which comes out soon. And in terms of really assessing the true holistic greenhouse gas benefit of natural gas as a fuel. So just to summarize, I think we've identified heavy-duty vehicles as a key sector for the UK to think about on its decarbonisation journey. It is important. Cars obviously are a bigger fraction right now, but we see that heavy-duty vehicles will become a more and more significant proportion of our CO2 as we transition to 2050. Between now and kind of this tipping point in 2035, we're trying to do what we can to accelerate low-carbon technologies which are market rational into deployment. I've taken you through an example of one of the technology developments we've done. We've talked about the whole systems perspective, and we're carrying on working in that way and trying to feed in real-world usage into that process. We're trying to seek people who are experts in heavy goods vehicles to help advise some of that. And also, I think it's because we have this kind of 2050, 2035 long-term energy system view, I think we can think about also how do we integrate our investments between now and 2035 with that longer-term world, such that we work our way to that so that we're only investing in infrastructure once, and we're only investing in R&D on vehicles once, because R&D availability is not easy for you guys, OEMs and tier ones. We recognise that. So that concludes my presentation. If there's any questions.
Excellent. Thank you very much. Are there any questions? Okay. One thing I'd like to ask you, Chris, is of course, the focus of the ETI is UK and Europe, but are you looking at the commercial viability of some of these technologies, and if any of them could already be deployed for example, second phase of greenhouse gas legislation in North America?
Yeah, I think that's a good question. We've focused on Europe because that's where we get our trucks from, and so we want to influence, the UK vehicle park. So we think about Europe. Obviously, increasingly, you've got Volvo, you've got Daimler, which have ties to the US market. I think some of our technologies and solutions, we need to do some calculations because obviously the US trucks go quicker and there's a different weight. So I wouldn't like to say that we are doing anything, and we need to do the calculations to do the value proposition, if you like, before we kind of step across to the US. But I think, we've thought about Japan as maybe a good starting point for some of this, as another kind of alternative to Europe. We want to focus on Europe, see how successful we are. I think if we struggle, then we'll look elsewhere to deploy the technology.
Mm-hmm. Great. Any questions? One at the back.
Study, very nice top down. I liked your slides at the beginning showing. Now, did I understand them properly? You're saying that the 80% CO2 saving by 2050 is non-negotiable, and then the dollars you put into your, or the euros that you put into your technologies to vehicle, you're on a law of diminishing returns. So what you're showing is that if you can have carbon capture to achieve your 80% non-negotiable CO2 saving, UK level, you don't have to throw so much more and more expensive, less and less beneficial technology onto your trucks to achieve your final aim. Have I understood that correctly, Chris?
I think so, yeah. I mean, I would probably flip
hard,
it
isn't it?
and say, there's effectively a carbon price needed to deliver that an energy system that meets that 2050 goal of 80% or less. And if you take technologies away, you don't deploy them, then you have to put something else in its place, which is more expensive. And so what we've tried to work out is kind of, okay, if the carbon price goes up, what does that mean on a per truck level? To then, as an opportunity to replace what you've lost because CCS has gone away. So I think yes is the answer. The 80%, is it non-negotiable? It's enshrined in law in the UK. Doesn't mean Parliament can't change the law. But I think Paris, that law existed pre-Paris. So you'd like to think post-Paris it should be more secure, not less. So I think we certainly see momentum building, but I'm not naive enough to say that can never change, But our job is to present and to try and inform about what that might look like and what the right steps are to minimise our investment as a nation, and to keep the burden on society as low as possible. And hence why we've kind of drawn those curves.
It's a really good example as how, as engineers, we should be thinking. It's very good. Thank you.
Thank you.
Okay, any final questions? Okay. In this case, thank you very much, Chris, for your presentation.
Thank you.
And we're right on time for lunch, which is here next door. We are back at 2 p.m. with a session on pathways to zero emissions. So enjoy your lunch, and see you all in the